Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
Hello again.
Today, we are strapping ourselves into the high-speed, high-pressure world of rotating machinery, what engineers call turbo machines.
And our mission really is to hunt down the fundamental principles.
Yeah, it's the elegant math, but also the harsh physical constraints that determine why a machine, a giant wind turbine or a tiny gas compressor, why it works.
Or why it fails. Catastrophically sometimes.
Right.
This is a deep dive into the absolute limits of efficiency, the violent physics of flow degradation, and the really clever control methods engineers are using now to manage instability. We've pulled from sources covering everything: hydraulic turbines, jet engines, you name it.
And what I find so fascinating is that these things, they seem so different. One's generating power, one's consuming it, but they're all unified by the same basic fluid mechanics. And we found this amazing common ground, starting with just one simple, almost beautiful theoretical limit.
That's right. This universal limit on power extraction. If we want to understand the maximum potential of, say, a wind turbine, we have to start with a concept called the actuator disk model.
I think this is a perfect example of engineering elegance, because you don't start by modeling every single curve on the blade.
No, you'd never get anywhere. You substitute the entire rotor with this theoretical thing, an actuator disk.
So it's a placeholder, basically.
Essentially, yes. It's imagined as this permeable plane that just instantly applies a force to the fluid. And that lets us model the whole system by just looking at the flow way upstream and way downstream.
Okay. And the power of this model, it comes from one big simplifying assumption about continuity, right?
That's the one. And it's actually quite intuitive when you think about it.
So let's break that down, because this is where the physics gets really powerful. The assumption is that the axial velocity right at the disk,
Which we call CX2.
CX2, right,
Yep.
is the average of the velocity far upstream, CX1, and the velocity far downstream, CX3.
Exactly. It just means the airspeed right at the blades is the perfect middle ground between what's coming in and what's going out.
Yeah.
Make that one simplification.
And you can derive this hard, non-negotiable cap on efficiency.
The famous Betz limit.
The Betz limit. It defines the absolute maximum power coefficient, CP, that a wind turbine can ever achieve, even in a perfect world.
And the number itself it's surprisingly restrictive. The max CP is 16/27,
Which is about 59.3%.
59.3. That's it. You cannot physically pull more than 59.3% of the kinetic energy out of the wind.
And you only hit that number under one very specific condition.
You do. It's when the axial flow induction factor, A, which is just a measure of how much the wind slows down, equals exactly 1/3.
So if you slow it down too little, you don't grab enough energy.
Right. If you slow it down too much, the air just flows around the whole turbine.
Yeah.
So performance drops off again.
This limit really shows why modern, lift-based turbines are the gold standard. They get close to this number.
They do. And it's why older drag-based machines, like those ancient Persian windmills, they're not really relevant for modern power generation. Their efficiency is just too low.
But our sources did point out some interesting exceptions, like the vertical axis turbines, the Darius or egg beater type.
Yes. Their big selling point is convenience. They work no matter which way the wind is blowing.
No need to yaw.
Exactly. But it's a classic engineering trade-off. You sacrifice that theoretical efficiency for operational ease. They have really low productivity near the ground, and worse, they produce these huge torque fluctuations with every single rotation.
Which has to be a nightmare for the grid connection.
A huge control challenge, especially in high winds.
That's a perfect transition, actually. We've set the theoretical max, but now we get into the messy reality of practical efficiency and physical failure.
And if we're going to talk about trade-offs, we first have to agree on how we're measuring success. Efficiency isn't just one number.
Right. The definitions matter. I saw total to total efficiency mentioned a lot.
Yes, you use that when the kinetic energy coming out of one stage is immediately used by the next one. Think inside a multi-stage compressor.
But then there's total to static efficiency. When does that come into play?
That's for when the kinetic energy leaving the machine is just lost. It's wasted. Like the exhaust from a jet engine. If that exit velocity isn't doing useful work, you have to count it as a loss.
And no matter how you define it, mechanical losses are always eating away at your performance. Things like bearing friction and windage.
Exactly. Windage is just the energy loss churning the fluid around the rotor.
Yeah.
And these losses can be surprisingly big, especially in smaller machines. We're talking up to 5% or even more of your total energy input just gone.
Just burned off as heat.
Yep.
But Few failure mechanisms are as dramatic or as genuinely terrifying as cavitation in hydraulic machines.
Oh, absolutely. This isn't just a loss of efficiency. This is physics turning into a wrecking ball.
What's happening?
Cavitation happens when the local pressure inside the fluid drops below its vapor pressure. So the water, it literally starts to boil at room temperature.
And it forms these little vapor bubbles.
Right, in the low pressure zones, often on the back of an impeller blade. Now, the bubble forming is no big deal. It's the collapse.
When it moves back into a high pressure area.
Precisely. The collapse is almost instantaneous, and it creates this incredibly powerful shock wave. Our sources cite that a single bubble collapse generates a pressure wave of about 400 megapascals.
400. To put that in perspective, that's like 600 times the pressure at the bottom of the Mariana Trench.
On a microscopic point on your metal blade.
Yeah.
Over and over and over.
I can't even imagine.
And that repetitive hammering physically removes material. That's cavitation erosion. It creates these little pits in the metal. You can even hear it. It sounds like gravel is running through your pump. Engineers call it white noise.
It's so destructive. But you mentioned there are ways to manage it. Super cavitating pumps.
Yes, this is where engineers get really clever. In applications like rocket engines, where size and weight are everything, they don't try to avoid cavitation. They encourage it.
They encourage it.
They design the blades to create a huge, stable vapor cavity that extends way past the metal impeller. The violent collapse point is moved downstream, away from the hardware. It's managing the violence instead of trying to stop it.
Incredible. Now, switching back to aerodynamics, not all degradation needs a 400 megapascal blast. Sometimes all it takes is a little dirt.
Blade fouling. It's shocking how big a deal this is, especially for stall-regulated wind turbines. It's an often overlooked factor.
So how big an impact are we talking?
A few percent.
Oh, much more. The data suggests that annual energy losses in the U.S. alone, just from increased surface roughness, are somewhere between 20 and 30%.
Wait. 20 to 30% from a layer of bugs and dust. That's astounding. It is. It just tanks the performance. The fouling trips the boundary layer, it causes premature separation, and your lift just disappears. And the sources point out it's even worse for small turbines.
Why is that?
The relative roughness. The thickness of the bug guts is a much larger fraction of the small leading edge radius.
So nature is constantly trying to wreck our designs. How do engineers fight back? This brings us to flow control.
And to the main battleground in axial compressors, which is managing flow diffusion.
A compressor's job is to slow the air down and raise its pressure.
Right, but you can't do it too quickly. If you try to decelerate or turn the air too sharply, the flow separates and you get huge pressure losses.
And that's why compressors need so many stages compared to a turbine, which is accelerating the flow.
Exactly. Push those limits too far and you get instability, you get stall, and potentially surge.
And the sources made a clear distinction between two types of stall.
Yes, you have blade stall, which is what you'd expect, flow separating from the airfoil itself. But then you have wall stall, which is connected to the boundary layer on the outer casing.
And knowing which one you have dictates the solution.
It does. If you're prone to wall stall, you can use something called casing treatment. Basically, you cut grooves into the outer wall to re-energize that sluggish boundary layer and delay the stall.
That sounds pretty smart, but what's the trade-off? There's always a trade-off.
The penalty is efficiency. The more effective the casing treatment is at pushing back stall, the more it hurts your stage efficiency right at the design point. You're sacrificing peak performance for a bigger stability margin.
Which is what's pushing the industry toward active feedback control.
That is the cutting edge, moving beyond passive grooves. These active systems use sensors like hot wires and tiny actuated vanes to monitor the flow in real time.
So they can see an instability forming.
They can see the tiny disturbances before they grow, and they can actively dampen them out, stopping a full-blown stall before it even starts.
Does it work?
The studies show it does. It can increase the stable flow range of a compressor by as much as 25%. It lets you operate safely, much closer to that theoretical limit.
So finally, let's talk about the designer's roadmap for choosing the right machine in the first place, specific speed.
Specific speed, or NADS, is a genius concept. It's a non-dimensional number, a shape number for the machine.
A shape number.
Yeah. It tells the designer what shape of turbomachine will be most efficient for a given job, a given head, flow rate, and speed. It takes the actual size right out of the equation.
So a low specific speed means you need a very high head.
Exactly. For really high heads, like 2,000 meters in a mountain hydro project, the specific speed value will be very low. And it tells you that you must use a Pelton turbine, an impulse-type machine.
And the opposite end, high specific speed.
That means low head, high flow rate. Think a river project. The number will be high, and it points you directly to a propeller-type machine, like a Kaplan turbine. It's the fastest way to get into the right ballpark.
It's interesting that for a certain middle range of specific speeds, the best radial flow turbines are just as efficient as the best axial flow ones.
They are. Between about 0.3 and 1.0, non-dimensionally, their peak efficiencies match up. It just confirms that getting that shape number right is what really matters.
What a journey. From the elegance of the Betz limit, that 59% cap, all the way down to 400 megapascal cavitation explosions.
It shows that engineering design is always this battle between the clean theoretical potential and the messy physical reality.
Right. You're using complex models like blade element momentum theory, not just to design for performance, but to balance everything else. Noise, cost, material, strength.
You're actively managing these unavoidable losses and fighting back against degradation and instability every step of the way.
So here's a final thought for you to chew on. Throughout this whole discussion, we've mostly used models that treat the flow as, well, as steady, time averaged.
Right, for the sake of analysis. But the reality is, the flow inside a turbomachine is fundamentally unsteady. The blades are moving past stationary vanes, creating wakes, pressure fluctuations. It's a chaotic environment.
So our best models are still just approximations of what's really happening.
They are. So consider this. How much higher could efficiencies go? How much more stable could these machines be if we could perfectly model and then actively control that inherent unsteadiness instead of just averaging it out?
That's a huge question.
That, I think, is the next frontier.
Fascinating stuff to think about. We'll leave you with that dynamic turbulence. Until the next deep dive.